All right, let's get started. Lesson 6, weak acids. Now, a monoprotic acid that's weak only has one hydrogen that is able to ionize in the presence of water or another base. So, for example, let's give you a generic equation. Let's say we have a weak acid, and it's going to represent by HA, and it's only going to have one acidic proton that's going to be able to be transferred to our base. In this case, it's going to be water. And because it is a weak acid, this reaction is reversible. All weak acids, unlike strong acids, are reversible. Remember, a definition of a strong acid is one that completely ionizes or dissociates in water, and there's no reversibility. But here with a weak acid, we actually have reversibility, and therefore an equilibrium can be established between the reactants and product. Well, if this is our acidic proton, that acidic proton is going to be transferred to the water, which is the base. So this is our weak acid, and this is our base, and we're going to form the hydronium ion as a result, which is going to be the conjugate acid, and the conjugate base, which is just A minus conjugate base. All right, all due to the fact that there's one acidic ionizable hydrogen, and that hydrogen is transferred to the base water to form our hydronium ion and our conjugate base A minus. Okay, now we can simplify this down actually even more. We can assume that water is the base, and if we can make that assumption, then we can actually leave it out of the equation and just take our weak acid HA, okay, which should be aqueous, and it dissociates down, and it is reversible to H plus the A minus. So this is our conjugate acid and our conjugate base. And remember that H plus really is the hydronium ion, just simplified down. All right, we're just assuming we know that the base is water, and so we can make that assumption. Now, if water is not the base, then you can't do this. You actually have to put the base into the equation. All right. So what are some characteristics of weak acids that you should be aware of? Well, first of all, again, weak acids are going to partially ionize or dissociate in water. Therefore, equilibriums can be established for weak acids. Unlike strong acids, remember, cannot form equilibriums. What are some common weak acids? Well, many of them have carboxylic acids. What do we mean by carboxylic acid? Well, usually in the formula, you have what is known as a COOH motif. And usually the COOH is bonded covalently to another group, and we'll just say R represents whatever. So you could have something like CH3COOH, where that is the carboxylic acid group bonded to the CH3 group. What makes the carboxylic acid acidic is it has one acidic proton right there, and that can be transferred to the base. All right, so these are common. You could also have something like CH3CH2COOH. All right, again, your carboxylic acid motif that gets ionized. All right. We'll discuss more carboxylic acids as we go through these lecture videos. All right, so magnitude. Oh, first of all, because weak acids form equilibriums, to solve weak acid problems, we must use ice. Just like we use other ice for other equilibrium problems, we're going to use ice for weak acids as well. Now, the magnitude of ionization or dissociation is determined by the Ka value. Now, the Ka value is like the Kc value, again, except for this is for the acid dissociation constant. So if you have a Ka value that is very, very large or greater than 1, we know that this is a strong acid. All right. If you have a Ka value that is super, super small, then you have a weak acid. Okay. So the smaller the Ka value, the weaker the acid, and the larger the Ka value, the stronger the acid. And you should understand that relationship. So, in other words, maybe another way of looking at this, as the Ka value goes up, the strength of the acid also goes up, okay, with increasing Ka value. All right, now, how do you also know if you have a weak acid? Well, you know the 7 strong acids. And if it's not one of the 7 strong acids, then it must automatically be a weak acid. All right, so let's go ahead and start solving some problems using weak acids and using the idea of the icebox to help us out with these, okay? So the first one is we have a student prepared a 1 molar solution of formic acid, and you'll see the formic acid has that carboxylic acid group to it. And what you want to do is find the pH of this formic acid, this 1 molar formic acid solution. Actually, they give you the pH. So the pH was found to be 2.38 of the formic acid. All right. Now, you should understand something about pHs of weak acids. When a pH is given of a weak acid, it is the pH at which the weak acid is at equilibrium. That's very important to note. So the pH here, since this is a weak acid, is the pH at equilibrium. So let's go ahead and start with a chemical equation. So we have formic acid, and so we're going to use the chemical formula there of HCOOH. Okay, it has 1 acidic proton that's going to be transferred. Now, because there's no base listed here, what do you think the base is probably going to be? If you said water, you'd be correct. Okay, so we're going to go ahead and put water in here as our base, and it's going to react and form a reversible reaction. And so we should form a hydronium ion and HCOO minus. Okay, so this is aqueous. Water is a liquid. Hydronium ion is aqueous, and our conjugate base is aqueous. So we have our acid, our base, then our conjugate acid, and then finally our conjugate base listed down here. Okay, now, since it is an equilibrium situation, to calculate the Ka value, we're going to have to use an icebox. Okay, so I'm actually going to draw an icebox out for this. All right, so we're going to fill in ICE. All right, now the equilibrium expression for this, and I don't have a lot of room, so I'm going to kind of write small. So Ka, which is what we're trying to find, we're going to take our reactant or products, which is the hydronium ion concentration, times the conjugate base concentration, all at equilibrium, divided by our weak acid, which is formic acid. Now, do we include water into the equilibrium expression here? And the answer is no, because water is in the liquid state, and you never add water to equilibrium expressions. So essentially in our icebox, we don't even need that because water is not even going to be consideration here. In fact, water is going to be overwhelmingly the essentially the excess reactant by far, and our formic acid will be the limiting reactant. Okay, so what do we know? Well, we know that we're starting out with a 1 molar solution of our weak acid. Our initial concentrations should be 0 for our products. The change in concentration is minus X plus X plus X. And we know that because everything is a 1-to-1 stoichiometrical ratio. So at equilibrium, the concentration should be 1.0 minus X, X, and X. Okay? Now, we have Ka that we have to find and X. So we have actually 2 variables that we need to calculate. So do we have any other information that could help us to maybe calculate X so that we can find Ka? And the answer is we do, and that is the pH. Now remember that the pH is equal to the negative log of the hydronium ion concentration at equilibrium. All right? So essentially, the pH, or the inverse log of the pH, is our hydronium ion concentration at equilibrium. So we can actually then solve for the hydronium ion concentration using the pH equation by taking 10 minus the 2.38. So this is going to give us our hydronium ion concentration. All right, and that should equal roughly 0.00417 molar. Okay, so our hydronium ion concentration is 0.00417 molar at equilibrium. Well, it turns out that that concentration is also our X value. Okay, so our X value, I'm going to write up here, is also equal to the hydronium concentration, 0.0041 molar. Okay, so equals X. Okay, as you can see from in our ICE table. All right, so now we know what X is, and so now we can go ahead and plug in X into our table here, and we know that this is going to be 0.00417, and this is 0.00417, and then essentially if we take our 1 minus our X value, so if we take 1 minus our X value, we end up getting a number of 0.996 molar. All right, and it's very close to 1, which we would think that would be the case, that since this is a weak acid, we don't have much dissociation going on. Okay, so now we need to, and I got to clean this up because I'm running out of room here. I'm going to go ahead and erase this. You keep it in your notes, but I'll erase it here. And I'm going to now find my Ka value by plugging in my equilibrium concentration. So 0.00417 times 0.00417 all over 0.996, and that will give me my Ka value. It turns out that Ka for this reaction is 1.75 times 10 to the minus 5. All right, so that's my Ka. And notice that the Ka value for formic acid is quite small, which tells us that it is a weak acid and very little of it is going to dissociate. All right, so that's how we use the icebox and the pH to calculate the Ka value. All right, now B of this is to calculate the percent ionization. How much percent-wise did our original concentration of our weak acid ionize? Well, remember, the original concentration of formic acid was 1.0 molar, okay? So how much of that ionized? Well, we know that X is the amount that was ionized, which was 0.00417 molar, okay? So how do we find the percentage? Well, it's simply this. You're going to take your X value over your concentration of your weak acid times 100. And that's the initial. So I'm going to put an I for the initial. So that means that we're going to take our 0.00417 molar over the 0.1 molar, or sorry, the 1 molar, 1.0 molar, times 100, and that will give us the percent that was ionized. In this case, it will be 0.417%. So only 0.4% roughly ionized from the original concentration. That isn't very much, but again, we should expect that very little ionization or dissociation would really occur for this weak acid because the Ka value is so small. All right, so that's how we determine the percent ionization of a acid or a weak acid. All right, let's do another problem. We'll do this a little bit quicker. In this case, now we're given the Ka value for our weak acid, and we're trying to find the equilibrium concentrations. Actually, not only the equilibrium concentrations, but we have to calculate the pH of this weak acid. So again, I'm going to start out with an equation where I'm going to take my weak acid, HCN, and since a base is not listed here, I will assume my base is water, and it will form an equilibrium with the hydronium ion and the cyanide ion, okay? Liquid, aqueous, aqueous, okay? So I have my acid, my base, my conjugate acid, and my conjugate base again, okay? So equilibrium expression for this, well, first of all, the Ka for this is going to be 4.9 times 10 to the minus 10. Now look how small that Ka value is. That's super, super small. That tells us that HCN is a very super weak acid. All right, and we can actually, in this problem, use the approximation method because of the small Ka value. All right, so we're going to draw an ice box here. All right, so initial concentration, change, and equilibrium concentration. Now, what is the equilibrium expression? So Ka for this should be the hydronium ion times the conjugate base over the weak acid. Again, water is not included because the base here, which is water, is in the liquid form, okay? So there we go. Now, initial concentration is 0.2 molar. Water we don't care about, 0 and 0. The changing concentration minus x plus x plus x. Equilibrium is 0.2 minus x, x, and x, okay? Now, we need to solve for x in order to be able to calculate the hydronium to get the hydronium concentration at equilibrium so we can figure out our pH. We need the hydronium ion concentration, this one value, to solve for the pH. Okay, so we got to have x. So if we throw x, or throw these terms into our equilibrium expression, we are going to use the approximation method because the x value has got to be really, really small. So therefore, this x right here, we don't need to worry about, because if we take 0.2 minus x, essentially that should be about 0.2. All right. So in my equilibrium expression, I'm going to put Ka. My Ka value I already know is 4.9 times 10 to the minus 10 is equal to x squared over, and that's from my products, 0.2. And I'm getting rid of that minus x again because I'm using the approximation method. So I'm going to solve for x. I'm going to take 4.9 times 10 to the minus 10, multiply that by 0.2 is equal to x squared. So essentially doing the math, I should find that 0.49 times 10 to the minus 10 times 2 is 9.8 times 10 to the minus 11 equals to x squared. I can get rid of the square by taking the square root on both sides. All right, and that should then give me my x value. X should equal essentially 9.90 times 10 to the minus 6, and that is really small, which should be expected. Okay, well, x is my hydronium concentration at equilibrium, so therefore I can say that the hydronium ion concentration is equal to 9.90 times 10 to the minus 6. Therefore, the pH, which is equal to the negative log of the hydronium ion concentration, can be found. We just plug x into our equation, and I will find that the pH is equal to 5.0. And that gives me my answer for this problem. All right, so there's another example of using the icebox, in this case to solve for the pH given the Ka value of a weak acid. Let's try one more. Here, one more example problem. So again, we want to calculate the pH, and the percent of ionization of HF. All right, so HF, weak acid, water is going to be our base again. So form the hydronium ion plus the F minus. Everything is 1-to-1 ratio. All right. The Ka value is given to us as 6.8 times 10 to the minus 4. Right. It's small enough. It's on the borderline, but it's small enough that we can still use the approximation method here. Right. So we're going to go ahead and make an ice table. All right, we don't care about water because it's a liquid. We start out with 0.10 molar, 0 and 0, minus x, plus x, plus x. We have 0.10 minus x, x, and x are equilibrium concentrations. Now, again, this x value right here can be estimated as being very small, so therefore we're going to ignore it in our equilibrium expression. The equilibrium expression, Ka, is equal to the hydronium ion concentration, F minus, over weak acid, which is HF. Right, so we plug it in. The K value, Ka is 6.0 times 10 to the minus 4 is equal to x squared over 0.10. Again, we're leaving off the minus x in estimation. So 6.8 times 10 to the minus 4, multiply that by 0.10 is equal to x squared. So therefore, this term should be 6.8 times 10 to the minus 5 is equal to x squared. Take the square root of both sides, and therefore x should equal 0.00825. X and the hydronium concentration should be the same at equilibrium, therefore the pH is equal to the negative log of 0.00825. pH turns out to be 2.08.
All right, and there's my answer. We would expect it to be lower in this case because the Ka value is minus to the -4, which is a much larger value than our previous example problem. So therefore, we'd expect more ionization to occur, okay? And speaking of that, so essentially this is just kind of how we go about doing this. Now we can solve for the amount of ionization by just taking our X value, which is 0.00825, divide that by the original concentration of 0.01 molar and times 100, and that will give us our percent ionization. And in this case, it looks like our percent ionization is 8.25%. Okay, is going to ionize here out of our original amount. All right, so there's how we solve example problem 3. Okay. All right, last little bit here, we're going to talk about polyprotic acids. Polyprotic acids have more than one hydrogen that can be ionized, okay? For example, let's give you H2SO3 aqueous. All right, in this case, both these hydrogens can be ionized. So the way we treat this is one ionized hydrogen at a time. So the first one ionizes to form H+, and assuming that the base here is water, so we're going to simplify this down and leave water out. So the acid ionizes down to H+, which of course H+ is the hydronium ion really, plus HSO4-, which is the conjugate base. All right, the Ka for this turns out to be 1.7 times 10 to the -2. All right, now we still have the conjugate base here, and this original one can still ionize because it has this second one that can ionize, making it polyprotic acid. And it ionizes down to H plus SO4 2-. Okay, can't ionize anymore the conjugate base. So the Ka for this one is going to be 6.4 times 10 to the -8. Now, normally the first ionized acidic proton is going to have a larger K value than the second one, as we see here. And so it's always easier to remove the first proton from the polyprotic acid than to remove the second. And if there was a third, the third one would be even harder to remove, right? So for many polyprotic acids, the Ka1, so that would be the Ka1, differs from the Ka2 by a factor of times 10 to the third. And if that's the case, then we can usually determine or estimate, and we do say estimate, the pH of the polyprotic acid by treating the acids if they were really monoprotic, and only considering the first ionization. So in other words, we're going to say that if the order or magnitude difference in the Ka values for the polyprotic acids is times 10 to the -3, then the pH is going to really be determined by the first acidic proton right there. And so you would use the icebox to calculate the H+ concentration of that, and then use that to determine the estimated pH. It won't be exactly the same because we still have a small amount of H+ for the second ionization, but most of it is the pH is contributed by the first one, okay? We'll actually do an example calculation of this in class, but I think this is good enough for now for this lesson. Please review your notes, study your notes for a quiz, and review this lecture video if you need to, but that is it for now.